We now discuss the solution of a problem from the section Linear Algebra that appeared in the CSIR National Eligibility Test held on 16th September 2022. The problem is related to Fibonacci-like sequences. The given problem is, let us define the sequence n belongs to n, of real numbers to be a Fibonacci-like sequence if an is equal to an-1 plus an-2 for n greater than or equal to 3. What is the dimension of the R vector space of Fibonacci-like sequences? We are given 4 options. Option 1, 1. Option 2, 2. Option 3, infinite and countable. Option 4, infinite and uncountable. Here is given the definition of a Fibonacci-like sequence. A sequence n belongs to n, is called a Fibonacci-like sequence if the nth term is equal to the sum of the previous two terms, that is an-1 plus an-2 for n greater than or equal to 3, and required to find the dimension of the vector space of all Fibonacci-like sequences over the real field R. We now discuss the solution of the problem in detail. We have the Fibonacci-like sequence n belongs to n, where an is equal to an-1 plus an-2 for n greater than or equal to 3. Now, the sequence n belongs to n, we write it as a sequence as first term, second term, third term, so on and so forth. That is the sequence a1, a2, a3, a4, a5. Now, we take the condition, Fibonacci condition, an is equal to an-1 plus an-2 from and after n greater than or equal to 3. Then we get a3 is equal to a2 plus a1. The next term, a4 is equal to a3 plus a2. For a3, we write the above a2 plus a1 plus a2, that is 2a2 plus a1. a5 for n is equal to 5 is a5 is equal to a4 plus a3. For a4, 2a2 plus a1. For a3, a2 plus a1. The sum is 3a2 plus 2a1. a6, a5 plus a4. a5 is 3a2 plus 2a1 plus a4 is 2a2 plus a1. So adding, we get 5a2 plus 3a1. Similarly, a7, you will get 8a2 plus 5a1, so on and so forth. So now let us write down the sequence, the term wise a1, a2, a3 is a2 plus a1, and a4, a5, a6. Up to that we have written etc. etc. Right. Now let V be the set of all Fibonacci-like sequences. So collect all the Fibonacci-like sequences, put it in the set, call it as V. Agreed. And it is given V is a vector space over R. You can take this as an exercise and prove that V is a vector space over R. It is not a difficult question. It's a simple question. Simple question. So you can see that V is a vector space over R, and anyway it is given to you. Right. Let an, the sequence n belongs to n, be any element of V. That means from V you take any Fibonacci-like sequence, any sequence you take. So that any sequence will look like, whose terms will be like this: a1, a2, a2 plus a1, 2a2 plus a1, 3a2 plus 2a1, 5a2 plus 3a1, plus so on and so forth. Then the sequence a and n belongs to n can be written as a2 times the sequence 0, 1, 1, 2, 3, 5, etc. plus a1 multiplied by the sequence 1, 0, 1, 1, 2, 3, so on and so forth. Thus we have written any sequence a and n belongs to n can be written as a2 multiplied by this sequence plus a1 multiplied by this sequence. And you may see these sequences are also elements of V. Why? Because they satisfy that property. an is equal to an minus 1 plus an minus 2. 0, 1, add 1, 1, 1, 2, 2, 1, 3, 3, 2, 5, 5, 3, 8. Like that you will get. And so also here. So these are the elements of V only. So that is equal to A2 multiplied by we call this sequence as the sequence Bn plus A1 multiplied by this sequence as the sequence Cn. So A2 multiplied by the sequence B1 Bn plus A1 multiplied by the sequence Cn, where Bn is this sequence and Cn is this sequence. Agreed. So what's that we have proved? This shows the sequence an is any element, arbitrarily chosen element. It means every element of V is a linear combination of these two sequences, sequence Bn and Cn. So what are you saying? That means every element is a linear combination of these two sequences. That means V is the linear span of B, where B consists of these two sequences, sequence Bn and sequence Cn. So thus every element of V is a linear combination of these two sequences. Therefore, these two sequences will generate V, and V is the linear span of this set B, where B consists of these two sequences. These are the elements of V. So now we claim B is linearly independent. So we have already seen B spans V. So we take B and we want to show that it is linearly independent. Then it becomes basis. Then we count the number of elements. That will give you the dimension. That is what exactly is wanted for the question. We continue in the next slide. We have V is the linear span of B, where B is the set consisting of these two bases, the two sequences, the sequence Bn, sequence Cn, and where the sequence Bn is this one, which belongs to V, the sequence Cn is this one, which belongs to V. And we claim B is linearly independent. For that, let alpha beta be any two real numbers. And alpha times the sequence Bn plus beta times the sequence Cn is equal to the 0 of V. That is the 0 element of V. So that is alpha times Bn, the sequence Bn we have written, plus beta times the sequence Cn we have written, and the 0 of the vector space V is also a Fibonacci-like sequence, that is 0, 0, added 0, 0 plus 0, 0, 0 plus 0, 0, 0 plus 0. So this is also a Fibonacci-like sequence which belongs to that, and that is the 0 element of V. Now multiply and add pointwise. Right. So scalar multiplication and added pointwise. We get this one. So these two sequences are same. So equating the corresponding terms, first term beta is equal to 0, second term alpha is equal to 0, and they are all zeros. So alpha plus beta is 0, alpha is 0, beta is 0, alpha plus beta is 0. So all of them are satisfied. And this will imply alpha is equal to 0 and beta is equal to 0. So this will tell you that B is linearly independent. We have already seen that B spans V, and B is linearly independent. Therefore, B is a B is equal to the set consisting of the two sequences, sequence Bn, sequence Cn is a basis for V over R. And what is that we want? We want the dimension of V over R. The dimension of V over R is equal to the number of elements in a basis of V over R. So that is n of B, number of elements in the set B, and these are the two elements are there, so it is 2. So the dimension of V over R is 2. Let's look at our options. Our answer, dimension of V over R is equal to 2, appears against option 2. Therefore, the answer to our question is option 2. And that is the detailed discussion of the solution of the problem from the section linear algebra, and the problem is related to the Fibonacci-like sequences. I am sure that you have understood the solution of this problem, and I wish you all the best. Thank you.